Okay, in this video we will talk about IV bolus. The model is called one compartment model, and we will talk a little bit about the introduction related to it and some of the definition before we go into details of the model and its equation. Okay, first of all, we need to make sure that we are talking about IV bolus, not IV infusion, and all of us know the difference between both of them. Okay, another thing, we will talk about one compartment model, and again, as I mentioned previously in one of our videos, then once I'm talking about compartmental model, by definition, I'm talking about conventional empirical model, just for short. So we are talking about compartmental model, and we are talking about one compartment model. So we will have one box that represent the whole body and all organs and tissue in the body. Okay, and we will have one kinetic process that is related to elimination. Okay, and I will mention or we will present the route of administration as a zigzag arrow to make sure that we are not talking about the any kinetic process, it's just the route of administration as IV bolus. Okay. We will talk about some of the symbols that we will use when we have dose that is taken. Sometimes you'll find it as X naught, okay, sorry for that, X naught as your dose, okay. Sometimes you find it as D naught, and it's the same, it's your dose or the initial amount. It's X at time of 0, so it's your initial given amount, okay. And by the way, I will try to be as slow as I can, as number of you asked me to be slower and the recorded videos, so I will try my best to be so. Okay, and for this one, it's again because we are talking only about IV bolus, so we will consider this arrow that is related to elimination process, and this is elimination rate constant. Okay, and we will talk about this in details. Okay, another thing, we will have something that is related to concentration of the drug in the body, and we will have amount of the drug in the body, and this will be at time t, and we will have a parent volume distribution, and we will talk about this too. Okay, we also have concentration at certain time measured in the plasma or the blood, and the same thing for the amount measured in the plasma or blood. Okay, so those are the symbols that we will use over and over, so make sure that you know them. So concentration of the drug in the body at time t, amount of the drug in the body at time t, apparent volume distribution, concentration of the drug at the measured measured concentration of the drug in the biological fluid, in this case the plasma, okay, or the blood, and the measured amount of the drug in the plasma at time t. Okay, so as we mentioned before, to have any model that we are talking about, kinetic wise, or any other model in general, we have what we call assumptions. Okay, and for our model in the IV bolus one compartment model, first that we mentioned that we are talking about one compartment model, and by default this is one of our assumption. And if we go back to the definition of one compartment model, we can find that the drug is under rapid equilibrium um, between or we have a rapid equilibrium between the systemic circulation and any other extravascular tissues or organs. That's why we are having everything in one box or in one compartment. So this is because we have, as we mentioned earlier, rapid equilibrium, or the same thing as rapid distribution of the drug in each and every organ, in addition to the systemic circulation. Okay, we have another assumption that it's the drug is or the model or the compartment, we call it well stirred compartment, or the model is well stirred model, or the drug is mixed instantaneously in the systemic circulation. And from the name of it, it's related to the stirring, as which means that the drug is stirred very rapid here in terms of instance when it's going inside the body. Okay, so again, the drug is mixed within terms of instance in the blood and the plasma. Okay, or in the systemic circulation. Okay, there's another thing that we are assuming for now, and we will talk about any other exception, that the model or the drug is following linear kinetic. And if we go back to first order kinetic, we know that the drug is, when we are talking about first order kinetic, it means that the drug is following, or it's another term of the first order kinetic. The drug is following a linear kinetic. Okay, the same thing. So if we are talking about this, again, it means that the drug that we are monitoring, let's say in the biological fluid, in this case plasma or serum, is under proportional relationship between, we have a proportional relationship between the rate that we are talking about, in this case elimination, and the concentration that is measured in the biological fluid, that we call it a linear kinetic, because we have a linear relationship. And this is what we mentioned earlier when we talked about first order kinetic, right? And first, this is just a reminder. First order kinetic, that the if you remember that the d a, we use this as amount equals minus k multiplied to a, if we are talking about amounts. And when we wanted to talk about concentration, it was d c over dt equals minus k multiplied to the concentration. So again, if we look about it, or look at this, or think about it, the rate under proportional relationship with the amount of the drug. The rate is under proportional relationship with the concentration of the drug. That's why we have this proportional relationship, and that's why we call it linear kinetic. Okay, and let's just I will talk about this, or I talked about this in a separate video. Okay, so again, we have to describe the model, we will have concentration, we will have amount, and we will have volume of distribution. But again, just let me draw this again. If we are talking about one compartmental model, and this is our compartment that shows or represent our model, we will have amount, and we will have concentration measured, and we will have a Barron volume distribution. Okay, and as we mentioned related to earlier in the experiments and sampling part, that we have difficulties experimentally to take samples from tissues. That's why concentration in the body would be not feasible, and the tissues are not accessible to do sampling, frequent sampling, as it's needed to have the profile concentration versus time. That's why we usually depends on the assumption that we mentioned before, that the concentration of the drug, the concentration of the drug at the measured biological fluid, let's say blood, is under, which is, again, this is an assumption, and we mentioned that this is one of the main assumptions that we usually use, and it's not right all the time, but this is one of the assumptions in this model, that the concentration measured in the blood or any biological fluid is under equilibrium with the concentration of the drug measured at different tissues and organs. Okay, and this is one of the main assumptions that we use to be able to, if we measure the concentration of the drug at the systemic circulation, to have some insights of whatever is happening in tissues and organs. That's why we will have measured concentration, okay, in the plasma or in the blood, and we will have some information about whatever is happening as amount of the drug in the body. Okay, and this is what we will use, one of the parameters to define this kind of relationship between the measured concentration and the amount that we have in the body. That's, again, it's not feasible to be measured directly because of the experimental issues that we talked about in tissue sampling. Okay, let's go back to the elimination and elimination rate constant. Okay, before we talk about this, we need to write the differential equation, right? So we will have amount in the body, okay, and we have IV bolus taken here, and we need to do whatever that we wrote before if we know that the drug is following linear kinetic. Okay, so just to remind ourselves of whatever that we know before, we mentioned before that if an amount of the drug that is eliminated, right? This is what we had in the part of linear kinetic or linear order, right? Let me just write it. Linear kinetic or first order kinetic. This is what we have. We have amount A, that is eliminated or decreased or changed to amount B. And when it was under linear kinetic or first order kinetic, we mentioned that we can write the differential equation of this as dA over dt, and this would be equal minus k multiplied to A. And we mentioned that this is the rate of change in amount of A versus or per unit of time. And this was amount of A, or amount of the drag at time t, and was first order rate constant, right? So let's do the same thing if we just keep this in mind as we know, and just let's do this for our model. So we have, according to whatever we just mentioned, we have amount in the body that is eliminated, and I'm telling you that we have one assumption that the drug is following linear kinetic. And again, this is an assumption, and we mentioned before that the majority of the drug is following a linear kinetic. Okay, so let's write the differential equation for this model. And again, if you just look at this, you'll be able to write it directly. I'm just changing the amount that we have to the symbol that we usually use in kinetic. So let's write the differential equation that we have. So it will be the rate of change in the amount of x over dt, that is equal minus k multiplied to xb. Okay, let's define each and everything that we have. This is the rate of decrease and the amount xb, which is amount of the drug that is in the body at time t, or in other words, its rate of elimination, right, of the drug, which is again the rate of decrease of the drug as amount per unit of time. This is first order rate constant, and this is the amount of the drug in the body or remained in the body at time t, okay, which is the time that we are talking about. Okay, so let's continue. If this is our differential equation, what can we do about it? Again, you can just go back to your first order class or notes or video, and you will see it's the same as we know. You can rearrange and integrate the equation, so you'll be able to have three different model equations. Okay, let's write them here. We will have the exponential equation, which is xb at certain time will be equal xb at time 0, which is the initial amount, multiplied to the exponent to the power of minus k time. We can have also the equation in the length term, which will be xb at certain time, which is equal to ln xb initial minus k multiplied with the time. The third equation, which is log xb naught minus k over 2.303 multiplied to the time. And again, if you go back to your notes, you can find the only change that we are using xp as the amount in the body. Okay, and for sure this is at time t, and this is the initial amount that we have. Okay, the same Let's draw it before we go back to the concentration. And as we mentioned earlier, we can draw each and every equation according to the model that we have, okay, or the equation that we have, sorry, and the graph that we are drawing on it, okay. So we will use rectilinear graph. We will use, sorry, similar graph, and we will use log, transform to log amount graph, sorry for that, and len. This will be on rectilinear, and will be in rectilinear. Again, I will draw xp, oops, xp versus time. I will draw xp versus time log xp versus time, and len xp versus time. Let's start with the first one. If we go back to our equation, this is the one that we will draw at the beginning, and it's either on rectilinear graph or on a semilog graph. So let's start with the rectilinear graph. We mentioned that as its exponential equation, okay, then we will have exponential profile, right? And it's mono-exponential profile because we have only one exponent term. That's why we call it mono-exponential profile, okay? Again, if I want to draw the same equation, the exponential equation, let's call this 1 and this is 2 as a profile, okay? Let's just change the number 1 and 2 and 4, okay? So let's go here, and if I want to draw this, and the only change that I'm having it on similar graph, so this will be as the y-axis is on log scale, as we mentioned, so we will visualize it on a log term, so it will be linear. This will be, because we are talking about IB bolus, will be x naught, right? And here your y-intercept will be your x naught, and this is for sure according to the equation that we have here, okay? So let's go back to the log term. I will not just transfer from here to the equation to the equations above, so I will write it here. Log xp naught minus k over 2.303 multiplied to the time. Okay, so again, we have y, we have x, we have the coefficient of x, right? And we have b. So this is your equation. This is y, this is x, we have the slope, and we have the intercept. And as we mentioned before, make sure that you know the signs that you have for the slope and the intercept. So accordingly, if I want to draw this equation, log xp at certain time versus time, this will be linear because we have a linear equation, right? And this will be log xp naught, right? And the slope will be equal to minus k over 2.303. And as we mentioned before, here is a real transformation of the y numbers or y amounts to log rather than just visually or visualizing it on a log scale. As we mentioned here, this will be xp, the profile, it's just drawing xp versus time at certain time, right? Which is the same here, xp versus time. The only difference between this one, which is number one, and number two profile, that this is on rectilinear profile and this is on a similar profile or graph. And here we just have a log transformation, okay? Which means that we are drawing what? Log log the amount. So log amount of the drug at certain time versus time. So that's why we are transforming the numbers that we have. We are not anymore drawing xp versus time. We are drawing log xp versus time. Okay? The same thing would be for, and it's on rectilinear profile for sure. The same thing would be for the len transformation. Again, this is len transformation, okay, which means that I'm transforming the amount that we have at certain time to its len terms versus time, okay? And if we write the equation, len xp, that's certain time, len x naught minus k multiplied to 2.303, okay? If we go back to our linear equation, y equals, this is mistaken. I'm sorry for that. This is multiplied to the time, okay? So this would be your x, this is your slope, and this is your intercept, okay? Y-intercept for sure, which is the slope coefficient of x and y. So if we go back to the profile that we have on a rectilinear a graph, we will draw len xp versus time. This is our y and this is our x. So let's draw it. Again, it's linear equation. So it will be like this. As a profile, it will be similar to whatever that you have here, but because you draw len xp, you will have here len xp naught, and the slope would be equal to minus k only, okay? And we need to make sure that if you are having the log profile or the log transformation, if you want xp or the initial amount in the body xp node, you need to take the anti-log of that intercept for sure. And if we want the xp here from this profile, we need to do anti-len of the y-intercept that we have. And if you, again, go back to whatever we mentioned here in the first order kinetic explanation and the previous videos that we have, you'll find that everything that I mentioned here is just a review for you to make sure that you already understand what you have. And again, we were talking in those equations about amount, right? And the body. So if we go back here, it was amount in the body. and it was amount in the body. Okay? And again, we just mentioned that it's not feasible for us to measure the amount in the body and different tissues or organs or whatever that we have at certain time. That's why we usually depend on the concentration measured in the blood or the plasma. Why? Again, because experimentally it's not feasible to do so. That's why we use the concentration measured, and we need a relationship between the concentration measured at certain time and the amount of the body at certain time. And again, those are the samples that we are having, and those whatever that we are interested in to know whatever is happening in the body. Okay, that's why we use what we call apparent volume of distribution, and we will talk about why we call it apparent later. Okay, distribution. Okay, as we know and we mentioned before, if you remember, concentration equals amount over volume, right? So what we will do, we will use this relationship to have the relationship between the measured concentration and the amount. That's why we'll have the concentration of the drug measured in the plasma, or the concentration of the drug measured in the plasma or the body at time t, amount in the body at time t over apparent volume distribution. Again, amount, volume distribution, concentration. But the difference, this is concentration measured at the biological fluid, in the biological fluid, and in our case, it's plasma, and amount in the body. So it's the volume distribution helped us to have this relationship to be able to know what is would be the amount in the body at certain time. So according to this relationship, we can have those equation, right? But in terms of what? Concentration. So let's write them quickly, but I'm pretty sure you can do that alone. So we have first one, which is the exponential equation, which will be concentration of the drug in the plasma at certain time, concentration initial, multiplied to e to the power of t. The second one, which is the log transformed, over 2.303 multiplied to the time. And the third one, which is the ln transformed, this is initial, sorry for that, minus k only multiplied to the time. And again, I will keep this for you to draw those four profiles, 1, 2, 3, and 4, but in terms of the concentration. So at each one of them, concentration versus time, log concentration versus time, ln concentration versus time, and just practice the y-intercept that you have and the slope for each and every one of them. Okay? One last information about the elimination rate constant that we are using in this model, which is K. It's your elimination rate constant. And in this model, we mentioned that the drug is following first order kinetic, right? When we are talking about first order kinetic, it means that the elimination is following first order kinetic or linear kinetic, right? So accordingly, the elimination rate constant is the first order elimination rate constant, right? The unit of the elimination rate constant according to whatever that we know, if it's following first order kinetic, would be 1 over time, or it's reciprocal, okay? And as we already know that the elimination would include two processes, right? Which is excretion and metabolism. So accordingly, if the drug is following a first order kinetic, which means that its elimination in this case, because only we have elimination, is under proportional or linear relationship with the measured concentration or amount. So accordingly, we can say that the elimination rate constant is a sum of all constants that is related to either to excretion and, not either, excretion and metabolism, if we have metabolism. So accordingly, it would be equal to Ke, which is one of the symbols for excretion, okay? And this would be excretion rate constant, okay, plus metabolism. So M here would be a short for metabolism, and this would be metabolic or metabolism rate constant. And again, if this is following first order kinetic or linear kinetic, it means that is this one would be first order and this one would be first order, to have this equation that all of them following first order. And again, we may have exceptions for this thing, so we will deal, for example, if they are not following some of the processes not following linear kinetic, we will deal with them as non-linear kinetic for that part of it. Okay, we will stop it here and we will continue about volume distribution